So you touched on, there's so much has happened, so this is class 2, so much has happened since then. But like you kind of almost unintentionally stumbled into the stochastic switch, right? So when you start actually handling batches and stuff like that.
Yes.
Maybe it'd be interesting to sort of start there because I think in the original formulation, actually, you have to run it on the whole. Am I wrong? I'm saying you're actually supposed to run it on the whole.
Yeah, supposed to run it on the whole thing.
Yeah.
There are no batches in the original one yet.
Yeah, right. So there's some surprisingly unintuitive things, I think, maybe about it, which is why that's such a natural follow-up, right?
You mean having batches?
Or
not having? I think having
batches is such a natural follow-up. No, or no? You don't think so?
I would say it's the other way around. Like most machine learning methods, you work on all the data, right?
But if you sure. I guess in a context where your data would be gigabytes or more, that becomes more silly. But
batches is like a more recent thing. In the whole machine learning spectrum, right? There's like one of the reasons for batches was to parallelize the gradient calculation. And the other point for the batches is like I have such a big data set, I cannot even read it into memory, and I want to process it also in parallel. This is where we go into like Spark ML, where you have some cluster grid, and then I do all the calculations in parallel, and then I combine all the outputs again, and then I can process huge data set in a very short amount of time. Well, depending on the size of the cluster.
Yeah, but also even at the time, if this is 86, you're looking at, it's not a Pentium.
Yeah.
What's the PC? Right? But yeah, anyway. That was a board. That was out. But we'll just.
It's hard for me to imagine, right?
Yeah.
So what was my first machine was, I think 100 megahertz, something like this. The first computer I had. It was like an Amiga, which my brother got. So I think it even had less than 100 megahertz, and it has like those floppy disks.
Right.
And like only a few megabytes of disk memory.
Right. So in today's sort of context, when it's like, I don't know, 11 gigabytes on my there's 11 gigabytes on my graphics card, and everything's being computed in parallel. I think we kind of forget the context that this is. Although I think you alluded to it. Anyway, that was my question.
So you want to mandatory mention Moore's law?
It doesn't have to be.
So, I would like it if you could elaborate on the ways to make gradient descent better, like these optimization methods to boost conversion, like just kind of like a general overview of what these functions are trying to do. Because I've used them in models, but I really have no idea like what's going on there. But
so, if you take the naive gradient, you're always what's it called, in 90 degrees to the slope. So if you have some like convex shape that's very narrow, what happens is you just jump around left and right, you never converge down in the hyperplane. And there are many things people came up to fix these things. One is like adaptive step size. So if I see I'm not really moving anywhere meaningfully, I just reduce my learning rate. Like I think in the paper they don't mention learning rate at all. So one thing is learning rate. So instead of taking the full gradient, and take a scalar, which is between 0 and 1, and I multiply it with the gradient. Maybe I just want to go 2% of the gradient. And the next step was, I think of ways of adaptively change my step size, depending where I'm located in the hyperplane. And next thing is, it's like having some kind of momentum-based technique. So the problem was that if you land in a local minimum, say you have like a very steep, and then there's a local minimum, and then there's a global minimum, you just run through. And then you might, if you just use normal simple gradient descent, you might get stuck in a local minimum. But if you use like momentum based, this is literally momentum in the regard like you would roll down a ball down a hill. So they have like a kind of speed going there, and it's going down, down. And then there's ADAM, which is like adaptive momentum rate, which combines these two things. And then there is another method which takes kind of a memory across all your gradients. So you take your first gradient, and then you multiply your second, like you take your current gradient, and you take the previous gradient, and you take a fraction of the previous gradient, and then a smaller fraction of the previous gradient before, and a smaller fraction of the previous. Yeah, that's momentum based, yeah, sorry. Yeah.
And a lot of these ideas a lot of these ideas also, just to add, they're not even originally, they come from other literatures as well, right? Like, but like particle swarm stuff was doing stuff with momentum ages and ages ago. Evolutionary programming had simulated annealing was the other one that had a temperature variable as well. So like a lot of these things actually come from other literatures and were added in. Well, we take it. We're like even at TMLS, they were taking something from holographic vectors. So there's a lot of cross-pollination.
Yeah, I imagine, because in general it's just like an optimization problem, which is pretty generic.
So,
but also given that, is there a lot more room to improve upon these methods, or is it pretty much solved at this point?
good question. Do you have any ideas?
I'm not looking for some.
People are still publishing. I think Jimmy Barr published a paper last year where he thinks of a more smart way of combining all the different gradients from a batch. So you run all your batches and you just take the average. It might not even be the best way. He's doing some kind of weighted combination with some kind of, I think, Bayesian priors. And this method was...
KFAC, if I'm not mistaken, that's the method. KFAC?
Yeah, KFAC. And this method come from physics or math, and it was actually really well known. And then he just applied it for these kind of gradients. So
it's a method that claims to compute the natural gradients.
Oh, right.
Because the normal gradients are, as Florian mentioned, they just go up and down.
The final one, so I'm sorry to take too much time here. Is there any particular rule of thumb as to which optimization method you would use based on what you're trying to do?
we start with Adam. I think Adam is very popular to start with, but it always these questions, they always pop up when you talk about hyperparameter optimization or you talk about like gradient descent or whatever. And I can just refer you to the no launch theorem, and you don't know how well your neural network will perform before you run it, right? If you know how your neural network or your machine learning model would work before you run it, then you can just, there's no need to running it, right? You would just use the optimal one.
Right.
So Adam is very popular for a start.
Okay, thanks.
We do have another video from the series on Eve that also covers like some of the other methods in that talk. So you were at some point you said a big important point about back-prop is the fact that it can be parallelized.
Yes.
Can you like essentially regurgitate that again, because I didn't get that part?
So in the paper they said back then, in that time, when all the neural networks were really small and all the data sets were really small and the second derivative optimization was viable, people just used second derivative optimizations instead of like some kind of gradient-based method. Because these gradient-based methods existed before. It was not applied for neural networks. And when they were applied for neural networks, they weren't applied in this kind of back-propagation way. So they calculated for each layer individually, and then they did some kind of conjugate gradients, if I remember correctly. And the gradient, basically this back-propagation allowed you to calculate the correct gradient for each layer. And the disadvantages of these first-order optimizations towards the second-order optimizations are globally. It's not restricted to neural networks. So the second order can always help you to point very directly to the global minimum, and if you can calculate it in a reasonable amount of time, you will optimize your neural network considerably faster. And the problem with the second order derivatives is, I can show you, and if you really want to calculate everything, so I show you this partial derivatives, right? So it's the first order. So basically, for each partial derivative, I have linear amount of partial derivatives, right? But if I want to do the second order derivative, I take the derivative of this and derive against this, and then take this against this, and this against this, this against this. So this is a 3 times 3 matrix, and if I really want to calculate the second derivative, the output matrix will be 9 by 9. But now neural networks have like 3.5 million parameters. So I want to have 3.5 million squared. I don't know how many particles are in the universe. Is it a larger or a smaller number? And and what people do because of this is that they do approximations of the second order derivative. They don't really calculate the full second order derivative. They just call only approximation. One is I only calculate the diagonal of the second derivative is one way, and there are other ways to do some kind of approximation of the second order derivative. And the power is here for the gradient that you can just calculate all the gradients in parallel, right? Each data point creates a gradient, and then if you take each data point and you do it naively, then you just sum up all of the gradients, right? And what you can do, you can just parallelize it for each layer. You run all your data on each core. Let's say you have 64 cores, you can split up your data into 65 data sets, chunks, and run it on each core. Or you have a graphic card which has 11,000 cores, and you split up your data into 11,000. Like, if you have 9 GB RAM, you just put as much 9 GB RAM into your data graphic card as you can, right?
Well, yeah, so I just wanted to add to
I think the back-propagation comes with the. Is it better?
Yeah.
It comes with the mini batches, because if it's just gradient descent you can, but with stochastic gradient descent for each mini batch you do an optimization, and then you go to the next step, and that's why you go up and down. But at least you can parallelize. Yeah, that helps.
I'm curious to know what data sets they were testing with at that time. I don't think they showed on the paper.
There were 2 data sets that described in the paper. And one data set was kind of like disease inheritance. So basically, do you have a disease, recessive disease or not, depending on your parents. And basically, the input data point was like your father has the disease 0 or 1, or your mother has the disease 0 or 1, and predicts if you have the disease. And then we're running it like many times. The data set was super small, it's like 112 data points, and then in the end they said it was kind of okay. I don't know, no, I don't want to, and it worked, I guess.
Yeah. Getting it to work is really hard.
Yeah.
Like if you go back one more paper, right? I think to the stuff that they were talking, like the Rumelhart stuff. You can see it's literally like you have 2 nodes, and you're like the that Zor thing. Like before this is Zor. Like how do we do Zor? Like I mean, okay, that's not exactly fair, but like the baby steps we're talking here is very tiny, like little. And also often semantic stuff, right? So everything is connected to everything instead of this process.
So before this, there was a huge conversation around perceptrons themselves. So we call these things nowadays multilayer perceptron, but that's not really a good name, because in perceptron, I think what you did, you added the loss or subtracted the loss from the weights directly. You didn't really compute the gradients. And it was usually people dealt with wider networks, so you didn't really have depth in your network, because it was harder also to compute. And it would act also weirdly. And one of the reasons that there was a drop in adaptation of AI, especially, and so AI kept going on. So oftentimes nowadays people think that like Jeff Hinton is AI. No, he's deep learning. AI was going on. He actually took the idea of hidden states from hidden Markov models that have been prominent in NLP. But to stay on the point, so this is an improvement because now you don't just naively add or subtract the loss to your weights, but you compute a gradient and it's more directional.
Or than just ask my question.
clap.
Oh.